So good morning, welcome to Sakala Vidya YouTube channel. Welcome Sai Kumar, welcome Pavitra. Okay, today we are going to discuss theorems on standard limits. Theorems on standard limits. Theorems on standard limits. So first theorem. So let us write the statement. If n is a rational number, and a greater than 0, then limit extends to a x to the power of n minus a to the power of n upon x minus a equals to n times a raised to n minus 1. So this is the theorem. So we need to give the proof for this theorem. So first let us give the proof. Now. So proof follows. First case 1. Okay. Suppose n is equal to 0. For n is equal to 0, does it hold good or not? We need to check. Suppose n is equal to 0. So then limit extends to a x to the power of n minus a to the power of n upon x minus a equal to limit extends to a, in the place of n substitute 0, x to the power of 0 minus a to the power of 0 upon x minus a. So this will be 1 minus 1 upon x minus a. Limit extends to a. So that means you get 0. 0 means n value is 0. This is, you can write like this, 0 times a to the power of 0 minus 1 you can write. 0 into something. 0 is nothing but n. So n times a to the power of n minus 1. Even for n is 0, it is applicable. Next, case 2. Let us consider case 2. Case 2 means, in this case 2, can it be applicable for negative values? N, if n is a negative value, can it be applicable? That we need to check. Okay, now suppose n is a negative integer. N is a negative integer. So that means, say n is equal to something minus m, but where m must be positive, where m is a positive integer. M is a positive integer. Since m is positive integer only, negative into positive, it becomes negative. N is negative. So now this limit x tends to a, x to the power of n minus a to the power of n upon x minus a. Now in the place of n, let us write so minus m. Limit x tends to a, x to the power of minus m minus a to the power of minus m, okay, upon x minus a. Okay, sorry, one thing, case 2 I need to discuss. Sorry, case I need to discuss for positive integer first, after that negative integer. So after that we need to discuss for rational number. Okay, sorry. So first we need to discuss case 2. Suppose n is a positive integer. N is a positive integer. So then limit x tends to a, x to the power of n minus a to the power of n upon x minus a. So if you divide this x to the power of n minus a to the power of n by x minus a, or factors of x to the power of n minus a to the power of n, we can write like this: x minus a multiplied by x to the power of n minus 1, so plus x to the power of n minus 2a plus x to the power of n minus 3a square plus dash dash, you will be getting a to the power of n minus 1 upon x minus a. Now limit x tends to a, you can write this x minus a gets cancelled, common factor. So now we have limit x tends to a, x to the power of n minus 1 plus x to the power of n minus 2 into a plus x to the power of n minus 3 into a square plus so on dash dash a to the power of n minus 1. So now it's a polynomial. So polynomial means directly we can substitute the limit. A to the power of n minus 1 plus a to the power of n minus 2 into a plus a to the power of n minus 3 into a square plus so on dash dash a to the power of n minus 1. See, this is a to the power of n minus 1 plus a to the power of n minus 2 into a. A to the power of m into a to the power of n is a to the power of m plus n. N minus 2 plus 1. So n minus 1 a to the power of, here also a to the power of n minus 1 plus so on, you will be getting a to the power of n minus 1. Now you need to check how many number of terms are there. Obviously it will be n terms. So that means it is n times. Same number is added for n times. So that means you get n times a to the power of n minus 1. So for n is positive integer, limit x tends to a, x to the power of n minus a to the power of n by x minus a is equal to n into a power n minus 1. For positive integer values of n, it has been proved. Now case 3. Case 3. Suppose suppose n is a negative integer, so that means say n is equal to minus m, where m is a positive integer. So therefore then even for negative integer also we need to prove limit x tends to a, x to the power of n minus a to the power of n upon x minus a. Suppose n is a negative integer, say n is equal to minus m, where m is a positive integer, then consider limit x tends to a, x to the power of n minus a to the power of n upon x minus a equals to, we can write limit x tends to a, x to the power of minus m minus a to the power of minus m upon x minus a. Okay, so now we can write this one as like this. This is limit x tends to a, this x to the power of minus m, you can write 1 upon x to the power of m minus a to the power of minus m can be written 1 upon a to the power of m upon x minus a. Now in the numerator let us take LCM. So this is equal to x to the power of m, a to the power of m. Okay, let us take the LCM. This is divided by x to the power of m, a to the power of m, a to the power of m minus x to the power of m. This we can write 1 upon x minus a, limit x tends to a. Now let us rearrange the terms now. So now we can write, take minus common, limit x tends to a, x to the power of m minus a to the power of m upon x minus a, write down. Let's put the bracket into 1 upon limit x tends to a, x to the power of m into a to the power of m, write down. This is equal to, since m is a positive integer, see m is a positive integer, already we have done. See, if n is a positive integer, limit x tends to a, x to the power of n minus a to the power of n by x minus a is n into a power n minus 1. So this we can substitute now. So in the place of this we can write minus m times a to the power of m minus 1 multiplied by 1 a to the power of m into a to the power of m. A to the power of m into a to the power of m, a to the power of 2n. A to the power of m by a to the power of n is a to the power of m minus n. Okay. Next we can write this one as minus m times a to the power of m minus 1 minus 2m. So we need to simplify these two. So minus m into a to the power of minus m minus 1. But nothing but minus m is n. Minus m is n. So instead of minus m, replace n. So we get n times a to the power of n minus 1. So that means even you can apply, right, even you can apply for negative integers also. So consider case 4. So consider case 4. What is the case 4? Suppose n is a non-integral rational number. Non-integral rational number. Suppose if n is rational number, can it be applicable? That we need to check now. That means say n is equal to p by q, where p comma q are integers, and one more thing, consider q must be positive, q greater than 0. Right. So now that means let us substitute n is equal to p by q instead of in the formula. So now thus limit extends to a x to the power of n minus a to the power of n upon x minus a is equal to, in the place of n, p by q write down. So limit extends to a x to the power of p by q minus a to the power of p by q upon x minus a. But we should not write directly p by q times a to the power of p by q minus 1, but we need to convert into the as a power of positive integer or negative integer. That we need to do it. So this can be rewritten as limit extends to a x to the power of p by q can be written 1 of x to the power of 1 upon q whole to the power of p, that is p by q only, minus a to the power of 1 upon q whole to the power of p by x minus a. Let us suppose x to the power of 1 by q is equal to something, a to the power of 1 by q is equal to something. Okay, let us assume. So let us assume or suppose, no problem, x to the power of 1 by q is equal to y. Now x is equal to y to the power of q, because if you raise the both sides power to q, you get like that. Which principle do you use apply for substituting such values? So that's actually real number means it may be a natural number or even whole number, even integer, even it may be a rational number. That's why we have selected the cases, 4 cases. Say a to the power of 1 by q is equal to something b. A becomes b to the power of q. As x approaches to a, y to the power of q tends to b to the power of q. That means y tends to b. Now as x to the power of 1 by q, a to the power of 1 by q is changed in terms of y and b. So we need to apply this limit, y tends to b. limit y tends to b, x to the power of this is y to the power of p minus this is b to the power of p, x transfer y to the power of q minus b to the power of q. Here p comma q are actually integers. P may be negative or q is definitely positive itself only. So now as y tends to b means here y does not equal to b. Divide both numerator and denominator by y minus b. Limit y tends to b. Okay. Y to the power of p minus b to the power of p upon y minus b divided by y to the power of q minus b to the power of q upon y minus b. Already we have discussed limit x tends to a. In the case 2, case 3 we have discussed. X minus a is equal to n times a to the power of n minus 1. Limit y tends to b, y to the power of b, p, b to the power of p upon y minus b. The same limit can be applied to the denominator also. Limit y tends to b, y to the power of q minus b to the power of q, y minus b. This is equal to, we can write using this formula, p into b to the power of p minus 1 upon this will be q into b to the power of q minus 1. This we have the formula a to the power of m upon a to the power of n equals to a to the power of m minus n. So using this we can simplify this one. This we can write p by q, b to the power of p minus 1 minus q plus 1 is cancelled. So we have p by q, b to the power of p minus q. Okay. Now, so this can be written p by q, b to the power of 1 by q and all to the power of p minus q right now. So now p minus 1 right now. Okay. One minute. This is b to the power of p minus q. For example, from p minus q, if you take q common, what do you get? P by q minus 1. Am I correct? If you open up, you will be getting p minus q. So this is equal to, we can write p by q and b to the power of q times p by q minus 1. This we can write p by q times p to the power of q all to the power of p by q minus 1. Now what is b to the power of q? Let us check it now. See, the b to the power of q is nothing but a. So now instead of this you can write a, p by q into a to the power of p by q minus 1. So since p by q is nothing but n as for our case consideration, so now we can put instead of p by q n. So this equal to n times a to the power of n minus 1. Therefore we conclude like this: limit x tends to a, x to the power of n minus a to the power of n upon x minus a equals to n times a to the power of n minus 1 for every n belongs to rational number and a greater than 0. Hence it is proved. Hence proved. Okay. So based on this, tomorrow we shall discuss more. Okay. This theorem has been completed.